So here we are. I'm talking about the high-intensity proton beams in the Indian perspective. Now, why are we interested in high-intensity proton beams in India? There are several reasons, good reasons for that. One is the major interest is in the utilization of thorium in energy generation, because India has about 50% of the world's thorium reserves, and that should be utilized. And then, of course, also it can be used for high transmutation of actinides. That's for the fission waste products. For medical isotope production, medical proton or ion therapy, and used as a spallation neutron source, which has many physics issues, can be attacked with that spallation neutron source. So how we proceeded was that we use the capacity and expertise building through the Indian Institution and Fermilab collaboration and the Proton Improvement Project, PIP2, to develop our technologies and leverage the superconducting RF technology for higher energies. First, we did the warm accelerator in the initial stage and the super SRF cavities for the higher energies. So there is a stage-wise development of the proton accelerators and their applications. There are two major initiatives in this. One is at BARC, at Hawaii Atomic Research Center, which is first building a 20 MeV LINAC, and it's very close to completion. In about, I think, a few months to about half a year's time, we should be able to they will be able to complete this 20 MeV system. And then there's development of 3 MeV and 10 MeV stage at RRCAT, and final goal of 1 GeV protons, which is very similar to that of the PIP2 accelerator at Fermilab. And so this is the overall plan. I haven't put any timeline on this because there is, at the moment, the final document has not been prepared for this with the timelines. But work is on in both RRCAT and BRC. And this is, as I will show you in the next slide, the PIP2 accelerator block diagram wise, they're very similar in the units that come in. And so this is the overall, the approach is to get, final goal is 1 GeV with 10 milliamperes beam, proton beam. It's not an easy task. Even the PIP2 doesn't have this, the parameters of the beam current. It's lower, about 1 milliampere at the moment to start with, and pulse repetition rates of 50 Hertz. And so we start with the ion source, 50 kilovolts, the beam transport, low energy beam transport, followed by RFQ operating at 325 megahertz, followed by the MEBT, beam transport system, followed by DTL LINACs here to go to it can go up to 100 MeV or so, 150 MeV. Then the elliptical, there'll be the spoke, the half-wave cavities are there, spoke cavities, which is very similar to that in the Fermilab accelerator, PIP2 accelerators, and taken over finally by the elliptic cavities of beta 0.61 and beta 0.92. And this is the wish list of getting put the beams into a 1 GeV proton accumulator ring going into targets for the spallation neutrons. And so the possible stage-wise application would be at 3 MeV itself, you can use it for radiobiology experiments. We can have depth dose curve measurements for proton beams at the desired energy for the therapy purposes in the 70 to 230 MeV range, and then nuclear physics experiments at 1 GeV. Yeah, the PIP2 accelerator, if you see, is the block diagram wise. It also has the, before, in the initial stage, they have a RFQ, and then going to the 2 MeV, the half-wave resonator, NIBM cavities, followed by the spoke resonators of 0.22, followed by the spokes of 0.475, and then elliptical cavities of 0.647, and well, it was actually changed to 6.1, and this has been changed to 0.92, and going up to 800 MeV. So this is what prompted us to get into the collaboration agreement. In fact, Swapan is one of the guys who he was instigator in this, And we met in 2005, and that's how we got in touch with the Fermilab, and the collaboration started forming. And finally, it was formed in 2007. And for the first 5 years, I'll describe what all has happened as I go along in the years, and how the technologies have been developed at the various centers in India. So this is the 20 MeV high-intensity LINAC at BARC. It starts with the ion source, with the ECR ion source at 2.45 gigahertz, 50 MeV. It's designed for extracting 60 milliamperes of protons, and they have successfully extracted up to 42 milliamperes at 40 kilovolts from this ion source. And followed by 352 megahertz 4-vein RFQ of 3 MeV. This has also been performed, has been built and extracted. And the 4 tanks of drift-tube LINACs at 352 MeV, 352 megahertz, and going up to 20 MeV. And this is almost ready now. I'll show you some of these components which is there. 3 MeV, this RFQ, 2 milliampere proton beam have been accelerated to 3 MeV with 65% transmission to this. So this has to be optimized, because finally, when you run for the actual purpose of generating the radioisotopes at the 20 MeV, we don't want to waste this kind of transmission, but this has to be optimized. This is the first result that was obtained. Then for the detailed tank, it's a prototype of this, and through the first tank, 6.8 MeV was achieved with a peak beam current of 2.5 milliamperes, and with 1 micrometer average current at 93% transmission. This was in February this year, but following that, in fact, about 2 months ago, and at the moment, currently, the tank the beam has gone through the tank 2 to take it to 12 MeV. The protons have been accelerated to 12 MeV, and then the tank 3 and 4 are being tested right now. And should be in any time now. We expect it could be a month or 2, or maybe I would say maximum of 6 months. We'll get this completed at BRC. So they go along the powering systems for these things. Also, the RF system development has been taking place at BRC. I'm talking about the development work towards the proton LINAC at BRC at the moment. Then I'll go over to the other institutions, what they're doing, contributing. Power amplifiers, it started in stages. These are solid-state based power amplifiers, 1 kilowatts, 3 kilowatts, 7 kilowatts, and 20 kilowatts. And you can see the parameters are given here. In fact, one of these, the power supplies has been now given to the Electronic Corporation of India Limited, so they will be able to produce in a mass scale. Industrialization has taken place. At RRCAT, they built 2 different types of sources. Again, this information you can, I think Vinith can, if there's questions or details of this, I'll refer to Vinith, who is here. The ECR sources, the 10 milliampere proton beam current at 35 keV beam energy from the ECR source has been extracted, and from the multi-cusp arc-based H- ion at 12 milliamperes for 50 kilovolt. This they have also developed the RFQ. I missed that. There is no. I thought there was a. There is RFQ. The development, 3 MeV RFQ development is going on in parallel at RRCAT as well. And then the DTL tank at this same 352 megahertz prototype drift-tube LINAC. And this particular one, it can go take beam from 2 MeV up to 100 MeV in range. It can accelerate. So then now I come to the superconducting RF development. It started actually way back in the first niobium cavities of not for the high energy, but for low energy heavy ions was developed at IISc Delhi. And we set up we had the complete setup of resonator fabrication. And then we collaborated with Fermilab and RRCAT to build the 1.3 gigahertz SCRF cavities. This is the ILC design, which the previous speaker was talking about. the same design from Fermilab, we got that. And the two of these cavities, one single cell cavities was built, and it reached about 40 megavolts per meter in the very first shot that we built them. This was tested at Fermilab. And after that, there was another one, which is for the spoke cavity that the half wave, the spoke cavities of beta 0.22, which will be used again in PIP2 accelerator. Two of these prototypes were built at IISc and then jacketed by BARC and then tested at Fermilab. And these also performed very well, much beyond much higher than the threshold of acceptance. And then some of these ILC cavities, 5-cell cavities, again jointly with the cavity fabrication machining was done at RRCat, and the welding, electron beam welding was done at IUAC. And then subsequently, before that, the VECC also is making the 0.61. They have the responsibility of making these 0.61, beta 0.61 cavities for the LINAC, for the PIP2 project. And again, they machine the cavities at VECC and bring it to IUAC for the electron beam welding. So this is the facility that we have at IUAC for resonator fabrication. We have the electron beam welding setup, the electropolishing setup, vacuum furnace for annealing, test cryostat, vertical test cryostat, and for high pressure rinsing, cleaning. So under this collaboration, PIP2 and Fermilab, Indian institution Fermilab, we have overall built the RRCat now decided, the DAE, Department of Energy, decided to invest in a big way on the SCRF infrastructure development. And this has been built at RRCat. The things are, we have got clean rooms, the vertical test cryostat, horizontal test stand, RF test stands, cavity processing facilities like clean room annealing, high pressure rinsing, and the entire cryogenics and vacuum stand setup. And the beta 0.9 and 0.92, the high beta 650 megahertz cavities and jacketing are being done at RRCat. The development of the tuners as well is continuing there. And they also have built solid state amplifiers with 40 kilowatts for powering these cavities. This is the collage of some of these setups that are there in the existing at RRCat. You have the electron welding and the various measurement checking for the precise precision machining work and testing. And these are the vertical test stand and the horizontal test stand where the full 5-cell cavity can be tested. First it is tested here and then sent to Fermilab for test. And I show the results of some of them. The very first 650 megahertz 9.9 cavity which is made by RRCat. It went to 19.3, which is the threshold limit, but then it quenched. But subsequently, this was improved. And then finally, when they made this 5-cell cavities, and there it went to this was tested at RRCat to go up to 1929 megavolt per meter with a Q of 1 × 10^10. And another one which was sent to Fermilab, this also went to for almost 30 megavolts. And you can see the Q value is also very good. That they are well within, they're much higher than the acceptable limit for the PIP2 project. And I think by now about 6 such cavities have been manufactured at RRCat, and they're all been tested. So the RF amplifiers which are built there, there's pictures of those at RRCat, 32 kilowatts and 40 kilowatts. This has been tested at Fermilab as well. And you can see this in the PIP2 project where India is contributing in this particular slide. And you can see there we are contributing right from here in the cryostat for this machine. And then we have single spoke cavities. India is contributing. I showed you pictures of those which were made. And initially, 2 of them has been made and performed very well. We have single spoke cavities at the first one is 0.22 and this is 0.45. This is the elliptical cavities, which are 650 megahertz. And then finally the highest beta is 0.6 and then this is 0.92. So we are completely in the line. And this project is supposed to be the target date for the PIP2 is, I believe 2028 right now for completion. And it seems to be, on the way. And all the technologies, the technologies and the components have been all prototype tested, and now in that they can go in the production mode. So just to give the idea of what other technologies have been developed in India for the accelerators, it is not part of the Proton projects, but we have some developments on the magnets, superconducting magnets, and helium liquefiers. So this is a picture of superconducting magnet which was made at VECC. The big cyclotron, superconducting cyclotron, was actually wound. The magnet was wound is a machine outside and then brought in, and actual winding was done on site at VECC. So that facility exists. You can make very large superconducting magnets there. And then the high TC superconducting magnet also has been developed at IISc. There was a 6 Tesla magnet, small size magnet for a test cryostat for doing material science studies was developed with the high TC material. And there is the development of indigenous helium liquefiers at RRCat and BARC both. And so they have both succeeded in producing helium liquefiers in making things indigenously. So right now we have I would say the entire capability, technological capability has been built in the country for any kind of proton accelerators, and we can take over we are waiting for this 20 MeV project, LEIP, the low energy project accelerator at BRC to finally deliver the beam. And then I think the project, the DA Atomic Energy, Department of Atomic Energy will take up the project in overall, and then we can put the timelines from there. So that's where we stand today. So I summarized that I just presented to you the recent progress in the warm end and the SRF technologies in the country, the low energy beam transport, RFQ, DTL, the high beta cavities, and the even 1.36 gigahertz ILC cavities. They've all been prototyped and tested and found to cross the acceptance levels, and in fact surpassed it. Many of the performances surpassed the acceptable limits. And the necessary infrastructure for superconducting RF with the vertical test stands and the horizontal test stands have been created. 40 kilo, the RF amplifiers and the cryogenics required for that also exists in the country. So now with this base, we can now start thinking of real big machines and also collaborate with the international community. So thank you for your kind attention.
Very impressive. Very impressive achievements. So you have all the infrastructure. You can build the entire FCC, I think, which is infrastructure. So do we have any comments or questions? Rohini.
Yeah.
I just want to give Amit special thanks for making this talk possible, because this was a very important part of the.
Yeah, and you did a good job.
Very good job.
Thank you.
I was also intrigued. You have a 6 Tesla HTS magnet already,
Yes.
so that's a good achievement.
Amit?
Yeah.
So what is stopping to give us a timeline for this 1 GB machine?
Timeline for this, as I said, right now at the moment it is not there, but we are waiting. As
Because
I
all the
said,
components are being built up
Yeah,
to
component-
Hybita and all.
yeah, it's all there.
Yeah.
Now we are waiting for this 20 eV DAHIPA to give this final beam, that which I said in about a few months' time it will be completed, and then we write the project.
So
Put the
what, from
timeline.
your,
From my experience,
Yeah,
from
that's right.
guesswork.
Yes.
Yeah, I would say that if the funding is given, if the DAE gives the go ahead of funding, then right now I think in about 5 to 7 years we should be able to complete this thing. It should be possible to do it in about 7 years time from the word go.
And this has been talked about for a long time.
Yeah, Vinny wants
Already
to say something.
15 years into the game. So I think we should. Other question, I think.
Yeah.
Yes.
No, this is just to respond to the comment about the timeline. Actually, the main thing is the funding. I mean, as he also mentioned that once we get the funding, then there could be a timeline like T0 plus 10 years kind of thing. But probably getting to the stage of the funding itself is very challenging.
Okay, I think, Frank, we have to really abbreviate the lunch session to half an hour, unfortunately, because we have to start at 2 o'clock.